Okay, so the next step would be to solve that. So now we have recursion tree to draw. We start with Theoben. 4 units of 4. And then we got two things happening. There's a T of n minus 1 happening over here. And another over here. Each of them with 4 units of overhead. And the breakdown goes on. So this recursion tree would really start looking like a tree. Of course, these very big trees they kind of take up space on the board, so you're going to have to generalize sooner or later. So at the kth level, we have our T of n minus k. And we'd have a certain number of nodes. Now we can't figure out a certain number of nodes if we want the pattern. At level 0, we have one node. It's actually 2 to 0 nodes. Level 1, we have 2 nodes. Which actually turns out to be total 1 nodes. And at level 2, how much nodes do we expect? Right? So at level k, how many nodes do we expect? To the k nodes. Of course, this will all go down until we reach level n minus 1. Wait, let me just normally write something here. That's 2 to the k nodes. You have 2 to the k of them. So you have n minus 1 nodes. And then you have the base case. So that would be a recursion tree. Of course, right for your base case, you would have 2 to the n minus 1. Down here, you'd have 2 to the n nodes. Now, and here you'd have 2 to the n minus 1. Yes. Yeah, 2 to the k nodes. 2 to the n minus 1 nodes here. So, we are therefore in a position to write down the overhead at each level and therefore figure out the overhead that the function takes to execute in totality. Because we know at level 0, overhead is equal to 4 times 2 to the 0 OV. OV stands for overhead here, right? OV equal 4 times 2 to the 1. OV equal 4 times 2 to 2. OV here equals 4 times 2 to the k. So to figure out the amount of work done in that for that function to execute, we just need to sum out the total amount of overhead plus add the work at the base case. Summation from k equals 0 to n minus 1 of 4 times 2 to the k plus 2 to the n times 1. And what kind of series is that? It's a GP. So 4 times this to the power of that, up to that limit. So it's 4 times 2 to the n minus 1. Right? That's fun, right? From this, that to that. So there we have an exponential function. Here we see that n actually shows up in the power of the time complexity. So as n increases, then this thing is going to take much longer, and it's going to, the time complexity, the amount of time is going to go very fast as n increases with a function like that. What that's saying is that if n was something like 1, then the amount of time that the thing would take would be of the order of 5 times 2 minus 4, which is 10 minus 4, 6 units of time. If n was 10, we have 5 times 2 to the 10, 2 to the 10 is 1024, then we have something like 5,000 time units. So when we start getting into hundreds of items, then this thing would just explode in the time.